Thanks everybody. So today, I'm Thomas, I'm a data scientist with Quantum Black, and today I'd like to talk about Bayesian optimization. And in particular, I want to talk about Bayesian optimization and how it can be applied in your day-to-day work. And really, I want to get two things across today. Like one, give you a little bit of an overview and some intuition around these sort of algorithms and how they work. And second, give you more of a practical overview as well. So like really, okay, if you were going to work on Monday again, just so you could directly like start applying these kind of methods and see if you get some cool results with that. So these are going to be my two points for today. So I'll start with the algorithm, and then at the end of the talk, we'll talk a little bit about the practical aspects, like how you would do it and how you would code it up in Python yourself, and we'll take a very brief. I'll give you a very brief overview of all the different frameworks that are already out there, in case you don't want to code up your own implementation. But just to sort of paint the sort of general the setting we're in, I think roughly the modeling workflow for data scientists, you can sort of split it up in these three parts. And this is like a simplified view, right? Because I'm sort of ignoring the big part that comes before this whole the feature engineering on the left side, where you try to get in the data, where you try to wrangle the data, where you try to formulate the questions you want to answer, the hypotheses, all this kind of stuff. We're sort of like ignoring that today, treating that as fixed. And I really want to talk a little bit more about the model selection part, right? So we already have the data. We already engineered a bunch of features for the model we're trying to build. We've maybe already done some kind of feature selection, some prior filtering or anything like this. And really what we want to do now is, okay, we have the data, we have a target variable, and we want to try to model that data in the best way possible. And Bayesian optimization, so the algorithms I'm going to talk about today, this is like, it's one instance of a class of algorithms that you can use to do this kind of work. In general, Bayesian optimization is much more general than just this. You can actually use it to optimize any arbitrary black box function. But the focus of this talk is really, okay, this more applied setting where it's applicable to you as a data scientist. So we're in this model selection sort of realm. So usually, just again to make sure we're all on the same page, right? Typically, what we try to do here is we have some kind of performance metric, F, that's based on some kind of model or learner, M, and usually this performance metrics we estimate it on some kind of holdout set, right? Like we train or classify or model on the training set, and we want to see how well it does on data that we've never seen before. And typically, the model we're trying to learn on the data, it has some kind of hyperparameters that we can't estimate from the data. So we need to sort of specify them ourselves. One example for a classification problem, for example, could be that your model M is some kind of support vector machine, and as you may or may not know, a support vector machine has a bunch of hyperparameters. So you might need to specify maybe the kernel of the support vector machine, or maybe the regularization parameter. Maybe the kernel actually has hyperparameters as well, so you need to specify them. And what I want to talk about today is, okay, how can we sort of choose these hyperparameters in a systematic way? And again, so we have the model, and we have some kind of performance metric, right? We want to optimize. So in the case of classification, for example, you could talk about, okay, I want to maximize the area under the curve on a test set. So yeah, this is our general setting. We have the performance function f, a learner m. This performance function, because it depends on the model, and the model depends on the hyperparameters, really we can say, or out of sample performance, it really depends on like how we choose the hyperparameters of our model. And again, this is all conditional on the data we have, right? So I specified it here, but I'm going to drop that. I'm not going to mention that dependency again and again. It's specified on it's conditional on the training data. So typically, at least what I've been doing in the past is, and I think what most data scientists actually do in their day-to-day work is when they deal with a situation like this, is they use something like manual grid search. So what is manual grid search? What I've shown here is a loss surface of a support vector machine. I've plotted it as a function of two variables, right? So I'm looking at a support vector machine with a radial basis kernel. So that's two, and the most important part for this, if you don't know what this is, okay, we have a model. It depends on two parameters, a parameter gamma, plotted on the y-axis, and a parameter c on the x-axis. And what it shows is just the out of sample. It's the area under the curve on a test set, and higher values of the area under the curve are better. So we want to try and maximize this value, and higher values correspond with red, and lower values correspond with blue. So when you talk about manual grid search, what people do is, okay, let's just build a grid of all of possible values of our hyperparameters, and evaluate our out of sample performance for every combination of those parameters. So here, the stars are basically our grid points in this plot. So we build a grid, and we evaluate the loss function for every possible star in this figure. I mean, this works, right? Like you're basically sampling your performance function. So if you do this, you get a good idea of what it looks like, and then you can take just the point that corresponds to the maximum value. The problem is that this can be problematic in two ways. One is that maybe it takes a very long time to actually get a sample of your performance function. So in this particular case, this took maybe 2-3 seconds, right, to get one sample of the star. But I guess in more typical examples, it can take maybe on the order of minutes, maybe on the order of hours, or sometimes even days if you're training really big models on really big data sets, right? So in those cases, this might actually not be a feasible approach. And the other downside of this approach is that in higher dimensions, this becomes more and more infeasible thanks to the curse of dimensionality. So the number of grid points you can build sort of increases exponentially with the dimension of your hyperparameter space. So these are two problems, right? So basically this thing, or this approach, manual grid search, it works well in simple settings. So what can you do? What else can you do, right? So another approach to manual grid search is something called random grid search. And I think maybe some of you have read this paper. I think it was a paper by Benjo written in the context of like very deep neural networks, which have a very high dimensional hyperparameter space. And there, the authors of that paper basically argue that, especially in high dimensional settings, you need to random grid search is a better way of trying to find the best value compared to just manually trying to evaluate all the points. So for those of you who don't know what random grid search is, by the way, it's just again you have this loss service, and what you do is you just randomly choose points and evaluate your performance functions for those randomly generated settings. But this feels a bit stupid. Like I think it was a couple of months ago, and I was trying to build some model on some kind of data set, and I was doing this, and this felt really unsatisfactory because yeah, I'm just hoping to get lucky, right? I'm just hoping to, if you look at this plot, I'm just hoping that I sort of randomly get into this space of good performance, and there's no guarantee of us actually reaching that region of good performance. So I was asking myself, okay, is there a way that we can do this better? Like, because preferably, if you look at this, right? If you look at this plot, so we have evaluated 4 points here. If you look at this, I can sort of see, okay, in the top plot, or in the top part of the plot, you see, okay, I've evaluated 2 points there, but I get relatively low performance, like I get an AUC of around 0.5, 0.6-ish. Whereas if I go lower in the plot, I actually get better performance. So preferably, I would like, if I were to do this in an automatic way, I would like my algorithm to sort of see, okay, hey, you know, here, here there are actually low values here we don't actually perform that well. So and I see below I actually perform a lot better. So I sort of want to steer my algorithm into that region of better performance. That's something that to me makes intuitively a lot of sense, right? You want to steer your algorithm into a region where you get better performance. It means you're basically sampling in a more efficient way. So I was wondering, okay, how can I do this, right? And one way of doing this is through Bayesian optimization. And Bayesian optimization is an instance, is a specific type of algorithms that falls into a wider class of what's called sequential model-based optimization algorithms. And what this means, this is a very fancy term, right? But what it means is just like we have a performance function, and we are trying to build, what we're going to do is we're building some kind of probability model for that loss function that enables us to say, okay, we've just seen these values. Now we can sort of update our belief of where good values of the performance are. Let's steer our algorithm into that direction of better performance. And this is what sequential model-based algorithms try to do. They build a model of the performance function, and sequentially you try to move into that region of better performance. Now, what I'm not trying to do here is to say that you should always use Bayesian optimization, or that it's like a silver bullet that will always work for you. Doing this is only really beneficial in certain situations, especially because, like I said, in Bayesian optimization, we're trying to build we're building a probabilistic model over a loss surface. And building that probability model introduces computational overhead because we need to update our beliefs, do some computation. So it actually introduces extra overhead and extra complexity in our overall pipeline. So really doing Bayesian optimization only makes sense if you have a very, very, very high dimensional hyperparameter space, or if it is computationally very, very expensive to evaluate the out-of-sample performance. Because let's say the out-of-sample performance takes on the order, maybe it takes an hour to evaluate, right, for one value of theta here. Then it's actually not so bad if you spend 2 minutes trying to update your beliefs so that the next time you spend another hour trying to compute this thing, that you get a better guess, right? So in these kind of settings, it makes sense to think about, okay, about smarter ways, right? In simpler settings, so if you think back about this loss surface I just showed you guys a couple of slides back, in that particular setting, this is probably not the most efficient way of doing it, right? Then you can just do a manual grid search over the whole parameter space. But in other settings, especially in these two settings, this could be beneficial. And I think these methods, these Bayesian optimization algorithms, they've been especially useful in the context of very deep neural networks. And in those settings, these work really, really well. Now, this was sort of the general overview of the problems the setting we are in, the problems we are dealing with. So now I want to talk a little bit about this Bayesian optimization algorithm and build up some kind of intuition around this, without trying to go too much into the details of the mathematics behind this algorithm. So this Bayesian optimization algorithm, you can sort of divide it in three steps. Usually, you sort of seed your algorithm with a couple of handpicked or randomly evaluated points. So usually, you already have like some values of the performance function. So what you do, you use those values first to build a belief of the performance function you're having. Once you have that belief, you now know, okay, now you have updated your belief, and now you sort of have an idea of, okay, in this particular region there I have higher performance, in this particular region I have lower performance. Here I haven't evaluated a lot of points yet, so maybe it might be worthwhile to try and evaluate some points there as well. So what we then do, given that belief, so given our updated belief in the bottom, we are going to try and pick a new value for the hyperparameters to evaluate. And the way we do that is we're going to maximize some kind of like utility function over this belief that we're having. And once you've done that, you get a new candidate for your hyperparameters, and then you can go on and on and on. And usually you go on and on until usually you specify a number of iterations you do this for, or you can also build like your some kind of handcrafted criterion, right? Maybe if the performance function, if the consecutive differences in the performance functions become sufficiently small, then you can say, okay, I've reached some kind of optimum. Let's just stop it. Let's just stop it there. So this is the general overview of the algorithm, and I'll go into each of the three steps in more detail now. And in general, I just want to say that, okay, this is the Bayesian optimization algorithm, but in the general class of sequential model-based algorithms I was talking about, they follow a very similar pattern to this. Usually you have a performance function, you want to try and update, you want to try and build a probability model over, or no, you want to build some kind of model over that function. Then you go maximize some utility over that model you've built, and then you evaluate the performance function for your new theta. And the way in which these algorithms usually differ is in how you build the actual model of your performance function. But now we'll focus first on this. And what we do in Bayesian optimization is we use something called Gaussian processes to actually model the performance function. And the reason why we call this particular algorithm a Bayesian optimization algorithm is that we use ideas from Bayesian statistics to build that model. So we use the Gaussian processes as a prior for performance functions. We have some kind of likelihood model. So usually that's some kind of like normal likelihood over the values of your performance function, and then you can use Bayes' rule to iteratively update your posterior distribution. I will not go into too much details of the mathematics behind that, but I do want to touch upon these Gaussian processes because I think they're quite a versatile tool, and it's good to have at least a little bit of an idea of what these things are and how they behave, because they play a quite pivotal role in this particular algorithm. So how you can think about Gaussian processes is that they really are the generalization of a Gaussian distribution or a normal distribution, but instead of over real numbers, this is generalization of that over functions. And just like a normal variable is usually is completely defined by its mean and by its standard deviation, a Gaussian process is now completely defined by its mean function and its covariance function. And a way to think about these Gaussian processes is that instead of the normal distribution giving you a real number back, a scalar number back, now the Gaussian process gives you the mean for now the Gaussian process for any point of your performance function. It gives you back the mean and standard deviation of another another normal distribution at that point. I realize this is quite a lot to just digest, so I've put this plot here in the hopes that this sort of makes this idea a little bit more clear. So if you've already dealt with Gaussian processes in the past, you may have seen this picture before. But this really shows what I was just talking about, that the Gaussian process now returns. It's a function that at any point returns the mean and standard deviation of a normal distribution at that point. So how should you read this picture, right? So what we have here is we have the solid dark line here. This is basically the function we're trying to optimize, maximize, or minimize, whatever you're trying to do. So in our context, you could think of it as our performance function, perhaps. The blue shaded region is the probability model that we're building using the Gaussian processes. So what we're seeing is, at the point where we have, and the dark circles denote the actual points that we have evaluated. So you can see, okay, where we have evaluated the function, we are actually quite certain about, what the value actually is there. But in regions where we haven't evaluated anything, so here and here, we are much more uncertain about what's going on, which makes sense, right? Like we haven't evaluated in that region, so we don't know what's going on. So what does the Gaussian process do? So if you look at this point, for example, it says, okay, at this point, the values of our performance function, they follow a normal distribution with a mean given by this, which is thus given by the Gaussian process, and a standard deviation given by this. So at every point, like here, here, and here, you can build a normal distribution over the potential values of the performance function at that point. So, and this is how these Gaussian processes model the performance function. Does this make sense? Is this because it's so I'm not sure. I'm trying not to show any formulas here and bore people with the math on Saturday morning, but I really want to build up the intuition so you have a kind of like a general idea of how these things work. Because the maths behind this can actually get quite involved. It's interesting stuff though, but I think it's too involved for a talk right now. So that was sort of the first component of our Bayesian optimization algorithm, right? So remember, we have these three sort of steps in our algorithm. We just talked about how we build the probability model, which is how we do it. So which we do with Gaussian processes. So now the next question is, okay, how do we actually, given our probability model, given our current beliefs of the performance function, how do you actually choose a new point? So you can think about this setting. The dashed green line is our performance function. We have our probability model. We have some evaluated points. And the question here now is, OK, where am I going to sample next? Am I going to stick to this minimum I found over? What we're trying to do here, by the way, is minimizing this function. Are we going to stick to this region, or are we going to explore the unexplored regions? So how do we do this? We try to use utility functions. And in the context of Bayesian algorithms, they are usually called acquisition functions. And they sort of formalize in a mathematical way what is the next best guess. There are lots and lots of different acquisition functions, actually. I just want to talk about one in particular, which is called the expected improvement acquisition function. And what it does, what it tries to do is say, OK, it wants to formalize, OK, let's take the next point should be the point that in expectation is going to maximize is going to increase our performance the most. So if you look at this thing, this is again our performance function. This is what we're trying to maximize over, and this is the current optimum, the best value we have found so far. So we're really trying to maximize that difference, like how much better can we get given our current optimum. And the reason why people look at the expected improvement function is because given in this setting, given like the Gaussian process model, you can actually evaluate this thing analytically. Yeah. Sorry?
Why is it matched with 0?
Because you don't want to, because you don't really want to look at the negative things. You really want to look at the at points where you're going to increase, points where you're going to decrease. You're not really interested in that, right? So, cool. So you can actually evaluate it like this. And the reason why I want to show you this is because it sort of builds up. It can help you to build up some intuition around how this acquisition function actually behaves. Because if you look at this, what you want to do is we want to maximize the expected improvement. So we're going to look at this function and think about, OK, when is this function when is the value of this function going to be large or big or whatever? Well, there are sort of two ways where this can happen. One case is this term is going to be large, which basically means we want to sample a theta that we expect to have a much higher value than our current best value, or we're going to sample in a region where the uncertainty is very high. So this is sometimes what's called the exploration versus exploitation trade-off. Do you want to exploit a current region that's already optimal, or do you want to explore a region where you don't really know what's going on there? Because you don't know what's going on there, it might very well be that there's actually some kind of optimum value there, right? So sometimes it's actually worthwhile to look into that region. So if we go back to our earlier example, here, this is our setting. This is the actual, this is the expected improvement acquisition function. And you can sort of see that there are a couple of peaks here. One is the peak on the left one, which says, OK, hey, on the left side, we've already found some kind of optimal value. So I expect to improve there a lot if I just stay in that region and try to exploit that knowledge. But on the other hand, you can also see that on the right, we haven't really sampled the function there. So the acquisition function basically tells you that, hey, there's also some value in exploring the rest of your the domain of your function.
But in this case, you do have a bounded x space.
Yes. Yes. Yeah, true. But so this is usually an input, right? So x is the hyperparameter space. So usually, yeah, you kind of have to bound that off. before you start this. But which I think is a general, yeah, you always have this kind of issue, even with grid search, random search. In general, you sort of have to say, okay, in this domain, we're going to look for optimum. So this is how it works. So we use the Gaussian processes to model the performance function. Given our new belief, we can then use something like the expected improvement function to say, okay, we expect that this particular point will improve our performance function the most. So which gives us our new theta. And then we can just evaluate the performance function for that new theta and iterate and iterate, update our model again, choose the next best value, on and on and on. So this is how the Bayesian optimization algorithm roughly works. So that's one thing I wanted to talk about, right? Like how the actual algorithm works. So now the next question is, okay, how can I actually use this in real life easily, right? Like how easy is it to, okay, I have some model, I have some data, how easy can I actually use this? So, so there are two ways. You can either use some prepackaged module or you can try to code it yourself. So because I wanted to get some better intuition of how this actually works, I tried to code it myself. And I think most of you are probably familiar with the machine learning library scikit-learn, and they actually have they have a nice Gaussian process module in there as well. So you can use scikit-learn to actually implement this specific algorithm. So scikit-learn has this Gaussian process module, and the two ingredients you now need is, okay, you need to build the actual optimization routine and the actual the performance function you want to optimize. So your performance function could be something like this, right? You have a loss function. Let's say we want to optimize the performance of our support vector machine. So a support vector machine takes some parameters. Let's say, and our performance function is actually the cross-validated AUC in this particular case. So it can work on cross-validated performance measures and on holdout performance measures. You can make this. This can be a completely black box function, right? It could be a massive neural net as well. And then the second step is the actual Bayesian optimization routine. And here again, you see like the relatively I don't want to really say simple, but sort of clear API of this sort of algorithm, right? You have your Gaussian process, which is the probability model of your function, and then the algorithm just iterates. What we do is we update our current beliefs using calling model.fit. Then we want to sample the next, we want to determine the next best value. So the next theta is going to be, this is just a function that takes the argmax of this expected improvement acquisition function. And then you can sample the loss and then iterate, iterate, and iterate. So if you do that, so I've done this for the support vector machine I've been talking about. So the top plot is the expected improvement function, and the lower plot is the current, our current belief of the performance function actually. So if you do this iteratively, let's see if this works. You can see iteratively, it tries to sample new points. So first it only has 3 points, right? So it tries to explore the region a little bit. It explores the region a little bit. Now you can see it's still exploring, and now you can see, okay, it's starting to discover here. This is an optimal region. Here I actually get really, really good performance. So you can sort of see, it explores a bit first, here, 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 and then it zooms in on this optimal region of performance. And I thought this was quite cool, actually. Like, this to me feels a lot nicer and more well-behaved than just like randomly sampling points, just hoping for the best, hoping we win the lottery. So yeah, so that's that. That being said, though, Gaussian processes, like when I was first trying this out, like I was really hoping to find something that was just as simple to use as random grid search or manual grid search, right? Because let's be honest, that's also the appeal of these methods. They're just very, very simple to use. And I was looking into this, and the plot I just showed you, that's very satisfactory. It makes a lot of sense. But these methods are still very tricky. So you have to for one you actually have to think about the scale of your hyperparameters. So this meaning that if you have a learning rate parameter, for example, or a regularization parameter, for example, you don't really want to sample that on a uniform domain. You usually want to sample that on like a log uniform domain, because you usually prefer values like 10 to the power -5, -4, -3, -2. So this is something you still, you can't just throw in your problem into this algorithm and expect like magic to happen, right? You still have to think a little bit, okay, these are like the specific hyperparameters I'm trying to optimize for, so I need to specify that in the model. And like was to this question before, you have to think about the domain of your performance function as well. And then the other thing is, the Gaussian process itself has a hyperparameter, the kernel. So, and actually the behavior of this algorithm is very, very, very dependent on the kernel of your Gaussian process. And different kernels actually assume different things. So some kernels assume things around differentiability of your performance function, or periodicity of your performance function. So this is still something you need to think about. So I thought this was quite nice, you know, quite a nice algorithm, but still you have to think about to basically tune your performance function. You still have to tune the algorithm that tunes the performance function. So it's still a tricky problem, unfortunately. Now to wrap things up, this is my last slide. It's of course very nice that you can implement this yourself, because it allows you to really like understand the algorithm and how it works. I wouldn't really I wouldn't necessarily recommend you doing that if you really want to apply this in like some kind of production setting. So if you are really interested in that, then maybe it's a good idea to look at some of the open source packages that are available on the web. So things, so packages like Spearmint, HyperOpt are very nice and relatively straightforward to use packages that can allow you to use these kind of methods in a robust way. And again, like we talked about Bayesian optimization algorithms, or model-based optimization algorithms. But you don't necessarily have to assume some kind of model on your functions, on your performance functions. So there are also methods like Hyperband and SMAC that are actually model-free. Try to model this in a model-free way. And that's it. Thank you very much for listening. And if there are any questions, please let me know.
Okay, thanks for the talk. We have like more or less 10 minutes for questions, so I just...
So this seems to work well for continuous variables.
Yeah.
Unfortunately, not all hyperparameters are continuous.
Very true. Very true. So you can. So this actually ties back to the whole point about the kernel. So you can actually use the kernel of the Gaussian process to tell, okay, this part of the input space is categorical. This part of the input space is continuous. So so I think, and what I've seen, like if you look on the web, I've seen two ways people deal with this. One is they try to use it through the kernel, but I know there's some. I think it's like called a Hamming kernel, which you can use to do this, but I haven't done this myself. And the other way, which I find this less satisfactory, but I guess it works, is you let the algorithm propose a continuous value, and then you just floor it or something like this, which is not. I don't really like this, right? But it's a way to deal with this stuff.
Alternatively, you can imagine that this is a Bayesian way, but it's a search space.
Mm-hmm.
So you could also use maybe gradient search or what have you, any other model. You can maybe do a support vector machine that tries to estimate the value of...
Yeah. Very, very true, which I think is actually what HyperOpt does under the hood. So they don't have a Bayesian model under the hood. They actually have something that's based on random forests under the hood. Yes, these kind of algorithms, the sequential model-based algorithms, they are not limited to a Bayesian way. You can use anything to build some kind of model, actually, which is also quite cool.
Hi, yeah, thank you for the talk. The question is, have you tried to compare this Bayesian approach with random approach for some non-trivial data set and non-trivial algorithm? Like, is Bayesian find the same as a random search or not? And second thing is just to point that one of good things about random search, you can do it in parallel, and I imagine that you kind of cannot do this one in parallel.
Yeah, agreed. So I have not done this myself. So what I've done is just really trying to understand how it works and giving that back to you guys. But of course, there's a lot of work. Like I've read a lot of papers where they actually do this, where they try to benchmark this against a bunch of different optimization algorithms, as well as random search. I think what I found in general is that if you compare it against those other algorithms and just random search, it tends to find the optimum in less iterations, which is a good thing. But then I've also read some criticisms of Bayesian algorithms where they say, okay, the nice thing about random search is I can just parallelize it, right? So let's just, if you then parallelize random search, it might take more iterations to get the optimum, but computationally it actually takes less time because I parallelized it, because this is hard to parallelize, right? So I think this is like an area of ongoing research actually, like can you make this algorithm quicker or can you parallelize it? Because from what I read, I think I read a paper where they benchmarked it against running random search 3 times, and then you can actually see that the random search it can be quicker. So yeah, again, I think it's a trade-off, and I think it's something that's ongoing. There's a lot of, I think, research into that area at the moment. Hope it answers the question.
Hello, thanks for the talk. My question is, how well does this algorithm cope with randomness at training time?
Sorry?
So randomness at training time. For example, I'm thinking random forest, where for similar hyperparameters, for a small data set, you can get very different results just based on the randomness of the training.
Mm-hmm. So the particular algorithm I've talked about now, it doesn't, right? It doesn't take into account at all how long it actually takes to calculate the value of the performance functions. But again, there's research into this area. So I've read a paper where they sort of reformulate, I think they reformulate, sorry? Okay, so could, yeah? I see. I don't think it takes into account. I think that's a very tricky problem anyways, right? Because if your model is that sensitive to something like a seed, it means your data is, you have not a lot of data, or your data is very, very messy. So it's in general, I think it's a very hard problem. So this is not magically going to solve it, unfortunately, for you. So I think, yeah, that's my answer.
Thank you for the talk. Can systems like this be expanded into dynamic search in terms like reinforcement learning, for instance? Are you aware of any attempts to use this method in that direction?
It's a good question. I think there are. I don't know about it. I think I've read something around this in connection with like multi-armed bandits, but I don't know enough about it to actually answer the question. I might have some links to literature for you, where I think I read it somewhere. So if you're really interested in that, I'm sure I can look it up for you.
Hi there. You mentioned that the kernel choice is important, or
Yep.
maybe need to be tuned depending on the loss function.
Mm-hmm.
If you had, say, a whole class of loss functions, you wanted to minimize over every single one of those.
Mm-hmm.
So you had a whole set of problems, and you knew that the loss functions were in some way similar.
Yes.
So in their periodicity or in their characteristics. Could this automatically, could it train on a set of loss functions to pick the optimal kernel that can then be applied to the out of sample loss functions?
All right, tricky question. I mean, this is not restricted to univariate functions, right? So I think the output of your performance function could be multidimensional. So I guess you could use this definitely to try and optimize. Well, it's hard, right? Because what's an optimal value in a multidimensional space? Like if you have a multidimensional output, I mean, I don't know. I don't know. I think it's an interesting question, but I don't think I can give you the answer to that question actually.
Okay, so basically you have to make some sort of assumption about the optimal kernel.
I think, yes, you definitely have to, like, unfortunately, yes, you do have to specify this as well. Maybe in some meta way you can try to optimize that kernel, but then I think you need the kernel for the optimizer that optimizes the kernel, so then you're sort of back at square one, right? So I do think this is like, you're the problem you can't avoid, unfortunately. No free lunch.
Okay, thank you very much.
Yeah.
Do we have more questions? Okay, if not, let's thanks for speaking again.
Thank you.